Today, this presentation will be about the American Fuzzy Lop, which is a subset of fuzz testing. And this is presented by Blake Wheaton and myself, Corbin Balzan. So when you first search for an American Fuzzy Lop, this adorable little creature comes up, a domesticated bunny in North America. And as much as this is the king of the Google search results, when you look for the Fuzzy Lop, we'll be focusing on a type of vulnerability testing. And in this presentation, we'll be referring to it as the American Fuzzy Lop. This is the command line interface of the tool that we'll be talking about today. It was created by Michael Zaleski out of Google with the intention of bringing about unexpected user inputs in order to simulate crashes or behaviors and expose vulnerability in some code bases. Before we dive in, let's talk about fuzzing with first a definition and then an example. So fuzzing is automated testing and code execution with the goal of finding security vulnerabilities. As an example, let's say we have an entry source that accepts images from an untrusted input. This untrusted input being a user. The user could alter the file type, name, contents, anything similar to try and inject either malicious code or create a crash and wreak any type of havoc upon your software. And humans can go through, they can read the code, the program that they created, but penetrative testing is a way of verifying robustness and checking for corner cases or these unexpected inputs that a human wouldn't catch in their normal quality assurance checks. So fuzzing came about in really 1988 as part of an advanced OS class project. It had been mentioned as early as the 1970s, but it gained much more traction in 1988 as the idea of testing sturdiness in operating systems came about. And this idea was revisited through different Unix systems used at companies like Apple for their Mac OS features. And they started to realize early on the value that this had. In Mac OS X, for example, they found some features could have crash rates of 7 to 73% within their critical services and features. And so they could then notice those vulnerabilities and engineers could debug from there. And fuzz testing is used on almost all large modern applications at companies like Google, Microsoft, and Apple. So the ACM defines three main options for vulnerability testing: static analysis, manual inspection, and fuzzing. Static analysis is a straightforward process of checking through code for any large unexpected code blocks. Manual inspection is when a user looks through the code, like in code review or pen testing when an expert's involved looking for large feature vulnerabilities. And today we're diving into, of course, fuzzing, which is the repeatable execution of all kinds and variations of inputs. These can catch buffer overflows, crashes, and the bugs are then logged and verified later by an expert. The three kinds of fuzzing: black box, grammar-based, and white box. With some slight nuances here. Black boxes uses well-formed inputs that are defined by the user, where the application doesn't creatively make new patterns to test. Instead, they stay within constraints. Grammar-based is user-provided grammars that then specify certain parts to fuzz. And then white box is where it gets slightly more interesting. The tests are executed dynamically in a more exhaustive approach to push the boundaries and discover vulnerabilities like buffer overflows. And this is because white box systems systematically increase code coverage by expanding the input variability. And this is the type of fuzzing that we're focusing on with the American Fuzzy Lop that Blake will now be talking about.
Thank you, Corbin, for that introduction on software fuzzing. So the American Fuzzy Lop is, as the name suggests, both a breed of rabbit and a software fuzzer. There are a few details that which make AFL unique. First, the software simplifies evaluation of bug analysis. Some useful tools that come along with this package include a crash explorer, test case minimizer, fault triggering allocator, and syntax analyzer, all of which aid in the process of reviewing crashes and program anomalies. Next, AFL was built with various successful fuzzing strategies in mind, and as the creators of the software mentioned, it has street smarts. It also has an optimized performance. There's a relatively speedy time of compilation and execution of program with AFL. One slowdown that many fuzzers experience is the repeated exec VE system call with every tested input, for example. This fuzzer is able to exec VE only one time over the course of its analysis. It's also well documented. The developers include detailed step-by-step instructions and README files in nearly every subdirectory of the program's original files. And since AFL is an open source software, there is much documentation written by other users available online. Finally, this is transferable. So AFL can provide various intricate testing inputs for different types of software that may be more specific to the user's desired testing tools. And now on to our demo. So as you can see here, this is a Linux terminal. And the current command that we will be using to execute the AFL fuzzer is this. And to go through some of the key arguments here, AFLN is the directory that our input is stored. From here, we have a binary of a simple Linux program called PC, which prints the current running processes. And we'll be taking the random characters or the compiled characters from this binary file and inputting it into this fuzzgoat program, which I will walk through in a second. AFL out is the directory that our crash statistics will be recorded. And I will now show the fuzzgoat program. So an example of the vulnerable code is right here. So this code below, as it denotes, creates and dereferences a null pointer. The string is of length 1. And so one of the triggers that will cause an error is a null pointer dereference. And so there are a few of these vulnerabilities scattered throughout the code, but for the sake of time, I will not walk through all of them. And go back to our execution. Okay, so I will run this. And a vintage style dialog box pops up with various statistics, current runtime, the last new path and last unique crash, and any hangups. And another important feature is the number of total crashes and total number of unique crashes. So I'll go ahead and stop the program for the sake of time. And we'll now look at the AFL output directory. So it has another subdirectory called crashes, which we'll investigate in 1 second. And also you see various other files. One is the fuzzer statistics. And this includes basically all the information you saw on the graphical interface as the program was executed. Now if we investigate the crashes directory and the file, so currently we are looking at all the unique crashes that the program has seen thus far before we exited. And there are SIG 6s and 11s, it looks like, which SIG aborts and SIG segmentation faults. And it also has the various codes for corresponding to the input that it used. Okay, and that is our demonstration. So what does this mean? What does, or where does AFL fit into this grand scheme of computer security? As we have mentioned previously, the original purpose of this tool is to detect anomalies and programs' behaviors so that users or companies can make necessary changes to ramp up their security. However, AFL and other fuzzing software can be used as an offensive tool as well. An ill-intentioned hacker may select a program that they believe might be susceptible to an attack and run a fuzzing routine. After vulnerabilities are discovered, they will then be able to gain a better idea of how to go about an attack. So this brings up the point that just because there are advanced computer security defense strategies being developed on a near daily basis, it doesn't mean that there is a decrease in offensive attacking potential. Well, this concludes our presentation on software fuzzing and AFL. Thank you very much.